storming outside quite a bit, and what better way to pass the time than to read a book? I found this bad boy in a Goodwill the other day, and I accepted the challenge to get through 1,000 things we should know about space, 1,000 facts. And over here, sitting on the universe itself, we got our trusty laptop to fact check and explore ideas further. If something in particular catches my interest. So, here's something to get our feet wet. A tablespoon of neutron star would weigh about 10 billion tons. 10 billion tons in a single tablespoon of neutron star, which is the state of matter left over after, at the end of a star's life, of a particular type of star. I think it might be a supernova, but we'll definitely find that out as we go along. And then telescope dishes have to be made accurate to within 51 billionths of an inch, 2 billionths of a millimeter. Wow. And then if there's good seeing and not too much light pollution, I suppose we can see 2,000 stars with the naked eye. I like how they're self-aware there. Now discover the other 997 facts. And for any of you returning viewers, you know, we gotta light a candle or two. Tonight's gonna be two. Let's get it back into focus. And this is a cheesy mug I got when I went shopping at Target with Molly the other day. I got because as cheesy as it looks, it kind of does help me remember, even if by sheer repetition, to be grateful for what I got. So I figured it wouldn't hurt for me to have a couple sips of gratitude every morning. Alright. As far as I can tell, the book is not really arranged in any logical fashion. It seems to be leaning into the 1,000 random facts. The only way that they seem to be grouped are that they're categorized in 6 kind of topics: Earth, the Sun, and Moon, then the planets. Going outward, we got the stars, universe, I suppose facts about astronomy, and then space travel has its own topic. So whenever we see these symbols, and that's how the book is set up to have two topics per page. Whenever we see these symbols, instance, here we have the constellations, which falls in the stars category. So we have Earth, Sun and Moon, planets, stars, universe. The history of astronomy. It's like the day and night falls in the first category, Copernicus in the second, and moon landings in the last, about space travel. And they're going to give us a table of contents in two forms, where the first is by category, which just says it looks pretty mixed up, and the second here is not chronological, but in order, in page order here, so you can see all the topics at a glance. We're starting it off with small stars. Small stars of low brightness, and it refers us to the HR, Hertzsprung-Russell diagram, that categorizes all characteristics of stars. They fall along this particular line we'll get to later. Small stars of low brightness are called white, red, or black dwarfs, depending on their color. So, I don't remember hearing about black dwarfs. We have red dwarfs are bigger than the planet Jupiter, but smaller than our medium-sized star, the Sun. And our star is an average, brightness average. It fits in the most populated category of stars. It's not rare by any means. Most stars in our galaxy are similar to our Sun, so that's actually cool when you think about the prospect of alien civilizations existing. So red dwarfs are bigger than the planet Jupiter, but still smaller than our Sun. They glow faintly with about 1% or 1/100th of 1% of the Sun's brightness. No red dwarf can be seen with the naked eye, not even the nearest star to the Sun. The red dwarf, Proxima Centauri. Now, white dwarfs are the last stage in the life of a medium star. Although they're even smaller than red dwarfs, no bigger than the Earth, they contain the same amount of matter than the Sun, so they're very, very compact. And you'll see things are vary in density. Stellar objects do, but it's a useful dimension, a useful characteristic of a stellar, a cosmic object, is its density, as we'll see. So they're a medium-sized star, a dying medium-sized star. Our night sky's brightest star, Sirius, the dog star, has a white dwarf companion called the pup star. And that's another common pattern that we find as we look into the night sky at stars, is there's a lot of binary stars that are grouped in groups of two, paired off in groups of two, and sometimes even more than two stars. red dwarfs, I mean. Red dwarfs are bigger than Jupiter. Brown dwarfs are a little bit bigger than Jupiter. White dwarfs are pretty darn small, only the size of our planet, which is very tiny on universal scales. Yeah, brown dwarfs formed in the same way as other stars, but they weren't big enough, almost like a big Jupiter. Not quite big enough to start shining properly, so they just glow very faintly with the heat left over from their formation. And then black dwarfs are very small, cold, dead stars. So they seem to be the least active remnants of stars, and there's many different types of remnants depending on the size and the density of the star that they formed and evolved from. The smallest kind of star is called a neutron star. So white dwarfs are the smallest dwarfs, but the smallest kind of shining, intrinsically luminous object is a neutron star. And then here, the picture we've been staring at here is a black dwarf. It says here, black dwarfs are stars that were either not big enough to start shining, or they've burned up all their nuclear fuel and stopped glowing like a coal cinder. So they're maybe even smaller than brown dwarfs, which are essentially, I think, if Jupiter had about 10 times its mass, it would have been able to have enough gravitational force crunching down on its center to ignite a nuclear reaction at its core, a sustained nuclear reaction, which it would then probably be a brown dwarf. So let's actually take a look. Let's take a look real quick and see if we can't look up brown dwarfs. I guess I could go a little bit further. Okay, that's good enough, I guess. Oh, let's see. Black dwarfs. Alright, so a black dwarf is a theoretical stellar remnant, specifically a white dwarf that's cooled sufficiently that it no longer emits significant heat or light. So it's theoretical because the time required for a white dwarf to reach this state is calculated to be longer than the age of the universe. No black dwarfs are expected to exist in the universe. Now, the temperature of the coolest white dwarfs is one observational limit of the age of the universe. Interesting. Wow, so they use life cycles of stars, the stellar life cycles over here to predict the age of the universe. Essentially, they look at a population that we can see, such as stars, out in the cosmos, and find out what we can about their nature, and then say how many of them, what age do we think they are. And I guess they think that the universe is too young to have even had time to make black dwarfs. And then here it says black dwarfs should not be confused with black holes or black stars. black star is a gravitational object. There we got some thunder cracking in the background now. Is a gravitational object composed of matter. It's a theoretical alternative to the black hole concept from general relativity. So the theoretical construct was created through the use of semi-classical gravity theory. A similar structure should also exist for the Einstein-Maxwell-Dirac equation system, EMD, or a classical field theory defined in the setting of general relativity. A starting point for some work in quantum field theory. So I don't know if you guys can hear it, but the rain's starting up again. It sounds really nice. Just pattering on the roof. So the Einstein-Maxwell-Dirac equation system is the superclassical limit of quantum electrodynamics. That's one of the famous Feynman diagrams, which I can't even pretend to understand. And for the Einstein-Yang-Mills-Dirac equation system, which is the superclassical limit of the standard model. Okay. Apparently a black star doesn't need to have an event horizon and may or may not be a transitional phase between a collapsing star and a singularity. Wow. Okay. I just wanted to take a peek at this diagram here. It looked pretty interesting. Stellar life cycle. We got so it goes from a molecular cloud to, let's get zoomed in here, why not? Molecular cloud to protostars. Nice, okay. Let's make it a little dimmer, I guess. Cut me out of the picture. So we have the molecular cloud that looks like Orion's nebula right in there. That turns into protostars, which are singular points around which they just happen to come from the densest part of the clouds. Turns into kind of a gravitational well towards which, like a center towards which, all the nebulous gas and plasma slowly floats over millions and millions of years. Eventually enough accumulates in a single point to create enough gravity to become a star. Then we have a huge crossroads here, bottom which anything less than roughly about a tenth, a little bit less than a tenth, 8/100ths of the mass of the sun becomes a brown dwarf. What's going on here? Birth, main sequence, old age. Oh, okay. And then within each of these columns is the main sequence. Above 8 solar masses, we have a low mass star. So that's what our sun is. That turns into a red giant in the old age. Let's see if we can. Let's zoom out just a little bit. There we go. No, it doesn't want to do that. It's like. So the red giant evolves into kind of a fizzling out. Anybody who's seen my nebula and supernova video comparing from Elijah Bird's old book I have, saw that in my thumbnail there. So the death from the main sequence to tend to have less dynamic change going on, I guess. They have less energy in general, so they don't explode, they don't evolve as fast. I suppose the brown dwarf eventually just fizzles out. Very, very, very slowly. And there's that thunder again. So, so nice. It's so relaxing to me, at least. I love it. But the low mass stars, they change. Generally, as their core is fused, all their fuel, their main fuel is hydrogen and helium. And out of that, heavier elements are fused and created. But once all that fuel gets used up, the star starts to expand, and it starts burning off outer layers, so its gravitational binding is less tight. The rain's getting a little louder now. And then eventually, I guess a white dwarf forms out of that. And as the final layers of its atmosphere just fizzle, they bloom away from the center of the star. And you're left with a white dwarf, and potentially, I guess after long enough, a black dwarf. But there's other ways of arriving at a white dwarf, apparently. We could have a binary white dwarf, which, I suppose if you have a red giant circling around a white dwarf, enough matter gets absorbed at over about 1.4 times. Now, is that the mass, or is that millions suns? Million suns. I'm gonna say it's mass. So at 1.4 times the sun, a nova will happen. Enough matter just accumulates where the gravitational pull and constriction on the star can't contain it, and eventually the star explodes. And then I guess if enough matter, a lot of matter is captured by that white dwarf, larger than about 1.4 suns, you have a type 1a supernova. So not just a nova, but an explosion so immense and energetic it can be seen across millions, tens of millions, and in some cases billions of light years. Or maybe that's type 2 that you can see across that large of a scale, but type 1a is still really, really bright. And then here, anything. So all that was for low mass stars, less than about 8 suns. And then for stars much larger than our own, greater than 8 times our own star, they burn hotter, so they have a bluer hue to them. And eventually, instead of just a red giant, life. Saturn's moon, Titan, has plenty of evidence of organic life. This book was written in the early 2000s. But it's still roughly up to date, I would say. As far as I know, a limited bit I know. So its moon Titan has plenty of evidence of organic life, chemicals in its atmosphere, meaning generally that means it's carbon-based life, which is what we are. Most of our molecules in our body have a core component of carbon atoms in them. Life is only known to exist on Earth, but in 1986, NASA found what they thought might be fossils of microscopic living things in a rock from Mars, which I believe they discredited that. They thought maybe it might have been from contamination, but we can look that up real quickly. Life on Mars. Let's see. Life on Mars. Let me Control F 1986 real quick. There's no results found, so I don't know what this is referencing. Liquid biosignatures. Curiosity, sediment sampling. This might be that. 2018, NASA reported that Curiosity rover had found evidence of complex organic compounds from mudstone rocks aged about approximately 3.5 billion years old, sampled from 2 distinct sites in the dry lake in the Pahrump Hills of the Gale crater. The rock samples, when pyrolyzed, probably meaning pyro, burned, via the Curiosity sample analysis, Mars instrument released an array of organic molecules. Whoa! So when they burned them, the fumes had organic carbon-based molecules in them. These include sulfur-containing thiophenes, aromatic compounds such as benzene and toluene, and aliphatic compounds such as propane and butene. The concentration of organic compounds is 100-fold higher than earlier measurements. The authors speculate that the presence of sulfur may have helped to preserve them. The products resemble those obtained from breakdown of kerogen, precursor to oil and natural gas on Earth. So says NASA. Here it says NASA stated, these findings are not evidence that life existed on the planet, but that the organic compounds needed to sustain microscopic life were present, and there may be deeper sources of organic compounds on the planet. Wow. Wait a minute. In 96, did I read that wrong? No, this says 86. Yeah, it says 8. So in 96, the Martian meteorite, ALH 84001, a specimen that is much older than the majority of Martian meteorites that have been recovered so far, received considerable attention. Reported features. When it had features that are best explained by the rock having which doesn't really help reason through that argument, because that just pushes the origin back. Because regardless of where they came from, they had to have originated somewhere. Whether it was on an alien ship, in which case, where did those aliens originate from, or if it was organically on another planet. Either way, it still doesn't answer the question. So basic organic life, such as amino acids, have been detected in nebulae and meteorites. And huge lightning flashes may have caused big organic molecules to form on the young Earth. I have no doubt that might have created quite an interesting chemistry experiment billions of years ago. Earth is right for life because of its gas atmosphere, its surface water, and moderately Goldilocks zone warm temperatures. So Mars is the only planet that once had water on its surface, which is why scientists are looking for signs of life there. And there we go. Speaking of lightning experiments, although remember in our Mercury episode, drawing Mercury, which I will get back to eventually, drawing Venus, Earth, Moon, and Mars, I did believe that it said there were, in the polar region, where the sun never really hits, there might be reservoirs of ice, even on Mercury, as close as it is to the sun, and with as little atmosphere as it does have. The side facing the sun does get scorched, but the lack of atmosphere means no heat is trapped. So where the sun's light, therefore heat, doesn't reach water in the form of ice, may actually survive there. And we know that the poles, it's pretty awesome if you've ever seen it. The poles of Mars definitely has ice. Lots of it. It looks like, at least. Mars is the only other planet with water on its surface. Jupiter's moon Europa probably has water below its surface, which could spawn life. How amazing would that be if there were just these gigantic alien beasts, underwater, aquatic aliens, swimming under the ice surface of Europa, around Jupiter. So, our next section here, the label here indicates that it's regarding space travel, is spacesuits. And I never realized how advanced these suits really are. And when you think about it, the lack of pressure, lack of atmosphere, the extreme temperatures would make me like 100% panic if I was up there. One small puncture in the suit, and you're an icicle. So spacesuits, anyways. Just relax. I wonder how many people just woke up to that. You guys can go back to sleep. Don't worry. You're not an astronaut yet, at least. You don't gotta worry about that. Spacesuits protect dust called micrometeoroids. And yeah, remember, it's without a lack of atmosphere. You can travel really, really fast. You have no air resistance. If you just do your hand, wave your hand real quick, you feel the air resistance in your room wherever you are. Stick your hand out of a car going 80 miles an hour and you really feel the resistance. So without that obstacle, you could be in space and something could be traveling 30, 50,000 miles an hour. The space station itself, I know, is traveling like 17,000 miles an hour, I believe, so right by you, going right by you, very fast. Let's see, so the clear plastic helmet, yeah, let's give you guys a better view. Also protects against radiation and meteoroids. Oxygen is circulated around the helmet to stop the visor from misting. The middle layers of the spacesuit are blown up to gently hold the astronaut's body. Small astronauts actually have the room to float inside their spacesuits. That's pretty neat. At least that would help with claustrophobia. So the soft inner lining of a spacesuit has tubes of water in it to cool the astronaut's body or warm it up. There's gotta be so much technology and engineering that goes into that. The backpack supplies pure oxygen for the astronaut to breathe and gets rid of carbon dioxide he or she gives out. Oxygen comes from tanks which hold enough for up to 7 hours. 7 hours. The gloves have silicone rubber fingertips which allow the astronaut some sense of touch. Because that's always got to be difficult when you think about it. Just how hard it would be to sense your environment, navigate it without. We're so used to having our sense of touch to tell us about what we're up against. Various different gadgets in the suit deal with liquids, including a tube for drinks and another for collecting urine. Alright, the full cost of a spacesuit is about $11 million. $11 million. Although 70% of that, roughly 7 million, 7.1 million, I guess, is for the backpack and control module. So spacesuits not only have to provide a complete life support system, oxygen, water, and so on, but must also protect against the dangers of space. Okay, so now we're on to the famous, probably other than Einstein, the most famous scientist. Certainly before Einstein, he was the most famous scientist. Isaac Newton. Isaac Newton. Okay. So trying to find the ideal distance so you guys don't get dizzy. For me, I like it when I have a sense that I'm really close to whatever I'm looking at. So I like the close proximity. Isaac Newton, from 1642, born in 1642, lived theorizing he was one of the founding fathers of modern day physics. We literally call entire paradigms of physics Newtonian physics nowadays, because he was able to come up with equations that helped us very accurately. And until Einstein came along, the most accurately ever track and predict the motions of objects under mutual gravitational pull. So, on top of being a scientist, who founded essentially modern physics, pre-quantum mechanics, pre-relativistic physics. He was the core developer of that field. He also was the president of the Mint of England, the nation of England. He was in charge of managing and controlling the quality of the actual coins in circulation, of the currency, and minting, and the ratios of certain metals within the coins. And so he was a high up government official in the I guess finance area of the government. He was an alchemist. That's always interesting to me. He devoted a lot of his time to alchemy. He was a devout Christian, and also one of the founding fathers of modern science. So I feel like he's crucial to understanding the schism of science and religion. Newton's ideas were inspired by seeing an apple fall, supposedly, from a tree in the garden of his home in England. I think we can all use our own gardens. Might come up with better ideas. Newton also discovered that sunlight. Oh yeah, on top of all that, of being a head member of the English government and a scientist, he was also a mathematician who, by the way, just as a side note, founded calculus. Calculus did not exist before him and his contemporary German, I think, mathematician peer, Leibniz, Gottfried Wilhelm Leibniz, the philosopher mathematician. And on top of calculus and understanding the mathematics of gravity, he also greatly moved the field of optics forward by studying light. He discovered that sunlight can be split into a spectrum made of all the colors of the rainbow. And Newton's discovery of gravity showed why things fall to the ground and planets orbit the sun. He realized that a planet's orbit depends on its mass and its distance from the sun. And the further apart and the lighter two objects are, the weaker is the pull of gravity between them. It actually varies as the inverse of its distance. So, if it's twice as far, its pull from an object is 4 times less. The further apart and the lighter objects, weaker pull. Newton worked out that you can calculate the pull of gravity between two objects by multiplying their mass. Oh, that's what I was getting at. By the square of the distance between them. So, it's a function of the square. So, yeah. As you get twice, if you get half as close as you were from the sun is going to be twice. Is going to be the square of the distance. Sorry, I gotta get used to exponents. The pole would be alright, I wanted to bring up our guy here because I started confusing myself. So the force of gravity is a constant G. Constant G. I need to make this smaller so we can get it. There we go. And the two masses divided by the square of the distance. So if we have that distance, that would be 1/4 the force. Man, I couldn't conceptualize that in my head. I had to look at the equation to remember. Man, I'm getting rusty. I gotta work on my physics. Call decaf math and get some homework help. So the gravity is related to how far away and how massive the objects are by exactly the square of the distance. It's very interesting that he could not only recognize that the motion, the trajectory of something in free fall when you throw it in the air, the speed, the acceleration is directly related to how massive that object is, how massive the Earth is, and the distance from the Earth to that object, because he was able to apply that to the moon falling around the Earth. He recognized the moon as this massive object, very, 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 very far away, 220,000 miles away. He might have actually been able to work that out. Roughly. I think he did actually, yeah. And figured out that the moon is this gargantuan, massive object, a small little planet in itself that's falling, perpetually falling around the Earth. It's maintaining enough tangential velocity that it never hits the Earth. It always keeps missing the Earth, and the Earth is a sphere, so it always overshoots the Earth and maintains an orbit gravitationally bound to the Earth. And this equation, F equals G times mass 1 times mass 2 divided by the radius squared, allows astronomers to predict precisely the movements of every planet, star, and galaxy. And it was actually primarily using Newton's formula for gravity that Herschel discovered. Was it Neptune? Uranus. Herschel discovered Uranus, and then eventually in the late 1700s, someone else, John Gall, discovered Neptune, way beyond twice as far away from the sun as Uranus. Neptune and eventually Pluto, from their effects of the gravity they produced on other planets. So, there was like resonances, and we'll get into that later maybe. But yeah, it's interesting that we could find out so much without even seeing a planet. We were able to use like Saturn and Jupiter, and we could determine that their orbits were perturbed a little bit. And it wasn't just because the sun had different areas, different distances, different parts of their orbits when they knew the sun wasn't supposed to affect the planet's orbit. They recognized that there must be another massive body out in the solar system way beyond Saturn and Jupiter. Jupiter and then Saturn's about twice as far out, and then they eventually found Uranus, and once we could track Uranus, we could determine that its orbit as well was perturbed by some unknown planet, and that was found in the early mid 1800s. So Newton's three laws of motion show that every single movement in the universe can be calculated mechanically. And it wasn't until we realized that physics is altered by extremely massive bodies like huge stars and of course black holes much later. Newton based his physics and equations off of a relatively low gravitational environment, gravitationally perturbed environment. Our sun is a fairly small star, so it doesn't have the extreme gravity wells that larger stars and black holes and huge star clusters and on galactic universal scales galaxies might have. And Einstein was able to revolutionize physics, the Newtonian physics that we relied upon for a couple centuries to account for environments that are dominated by very, very much more massive objects than our sun. And in fact, it was Mercury being so close, being the closest planet to our sun, that was really the only planet, massive body in our local, solar system that was affected by the effects of relativity. And so, because it was so close to the gravitationally massive, dominant sun, its orbit, the light, as we see it, as we viewed it from Earth, was perturbed and slightly deviated from Newton's predictions in his mathematics that so precisely predicted all the other planets' orbits. And so we always wondered why Mercury had a unique, weird orbit. And once Einstein came along with special and eventually general relativity, we were able to determine essentially that was the huge confirmation that Einstein was incredibly correct and massively insightful in his theories of relativity. We understood that the sun's gravity warped the trajectory of light. And I think it was an eclipse of the sun, so the moon, when it eclipsed the sun, we were able to see stars. Let me use the candle here as a good example. Once the moon eclipsed the sun, we were able to see stars like as though that black dwarf was a star. We could now see that star during position, meaning its apparent position, where it appeared to lie in the heavens, in the galaxy, was different from what we knew it to be. And that was, it turned out, because the sun was bending its light. So as this star's light passed into our eyes, it actually went around the sun and was bent by the sun's gravitational will. And so we were over here seeing what was actually behind the sun, and it appeared to be over here. If it would have gone in a straight line, that's what it would look like. And that proved Einstein was right, that even gravity bends light. So we didn't get very far today, guys, but that's alright. We're here to relax. Ernie's definitely relaxing. He's fast asleep. You might hear him squeaking right there. He's dreaming something. He's chasing some lizards for sure. So I'll let you guys go, and we'll see you in part 2 out of who knows how many parts. So thanks for watching. If you're not asleep already, go ahead and get some rest, get some relaxation, guys. I hope you learned something. I hope this was interesting. Thanks for watching and supporting the channel.